Hello everyone, my name is Sohrab and I'm glad to share with you what I've been working on in the past few months. I was lucky to have the opportunity of getting started with InSAR analysis, and this presentation is about this topic. InSAR stands for Interferometric Synthetic Aperture Radar, and the general idea behind its mechanism was originally inspired by regular radars used to track aircrafts and ships through heavy weather and darkness. With the same theory, it can be used for monitoring the ground and track its displacement. Unlike telescopes that work in the visual spectrum of electromagnetic waves, SAR technology works in a different range, and to avoid very long aperture sensors, experts have come up with a signal processing technique to use a shorter one, and that is why the term synthetic appears in the acronym. But how does it work? The orbiting satellite constantly emits electromagnetic wave to the ground which illuminates a footprint on it. Objects absorb and scatter some of it and reflects back the rest of wave energy. Like any other waves, these waves have also an amplitude and phase. The amplitude component somehow resembles the aerial photographs, but phase component consists of speckles. Next time the satellite is passing the same point, it gets the second backscatter acquisition. If the phase of two backscattered waves is subtracted, a pattern of concentric ramps is obtained, known as interferogram. This interferogram can be transformed to displacement after certain steps of processing the stages and removing unfavorable layers. Different items play a role in creating an interferogram, such as topography. Atmosphere is also another factor that interferes with satellite waves, thanks to its ionized particles, which causes impacts on the interferogram. In addition to these, satellites do not capture SAR images at the exact same locations, and there are some orbital errors associated in this process. Random objects are arbitrarily distributed on the ground, and each has a specific reflectivity properties. Even if we can manage to deal with all these, the waves are wrapped in the range of -pi and +pi, and we need to unwrap it. When all these items are addressed, we will have the displacement then. However, this displacement is not the actual displacement, but only part of it. InSAR yields only the displacement that is projected on the satellite line of sight. The relationship between line-of-sight displacement rate and actual horizontal and vertical displacement rates is mentioned in top left. In this formula, geometrical features of the sensor is also involved: incidence angle or theta and heading angle or alpha. Theta is the angle that the vertical axis makes with line of sight, and alpha is the angle that satellite's flight direction makes with north. InSAR gives off the line of sight velocity, and to find the actual components, we need to find more line-of-sight geometries. Well, satellite sweeps the globe in two different geometries, ascending and descending, which is shown in figure 4. Having these two geometries, we will be able to attain the components of movements. However, it comes usually at the cost of ignoring one of them. Various computer programs have been developed for InSAR analysis, and I'm going to talk briefly about 3 of them which I worked with. The first one is a SNAP, powered by European Space Agency. It's free and user-friendly with so many resources, but on the downsides, it's not fast or seamless and cannot do time series analysis. Well, to compensate for the last one, people usually couple SNAP with the stamps. A SNAP can efficiently do initial stages of process, and that is when a stamps kicks in to do the time series analysis. However, a stamps is very challenging to set up, as it runs on the Ubuntu operating system and goes through the command shell. This brings us to the last software I worked with, and the one that I had the most success with, SARPROS. It has all we expect. However, it is not free, but they grant academic license upon reasonable request, at least based on my experience. Today I'm going to talk about my most recent analysis. The first study area is the famous Thompson River Valley. In a 1 kilometer section of this valley, numerous slow-moving landslides are moving on subhorizontal shear zones. Most of them traverse significant infrastructures, which highlights the necessity of surveillance on this corridor. Although I have partially analyzed most of them, I'm going to mainly focus on Red Hill and Ripley slides today. More than 300 SAR images archived by RadarSat-2 and Sentinel-1 were processed and studied here. The average revisiting time was 24 and 12 days respectively. On the right you see a plan view of the Thompson River Valley along with the flight direction of these satellites. Sentinel-1, whether ascending or descending, has a near polar orbit which makes a sensor least sensitive to north component of movement, but luckily we had the privilege of RadarSat-2 to compensate for this. Having three different geometries provided us the opportunity of obtaining three-dimensional displacement vectors. Here you can see a rough presentation of line-of-sight displacements after analyzing RadarSat-2 images. The extents of most active parts of this landslide were correctly detected. Light green indicate low magnitude of movements. Well, let's start with Ripley. On the left you see the vectors of horizontal displacement and the magnitudes are color-coded. This figure clearly shows the boundary of the Ripley's most active part. The results show that the Ripley has been moving with the average rate of 50 to 110 mm per year toward the Thompson River in years 2016 to 2021. These observations are somewhat aligned with our knowledge on this site. Previous studies have reported horizontal displacements up to 120 to 130 mm per year as well. Figure 10 on the right also displays the average total displacement rate in this period. Again, the boundary of most active part is clearly defined, and it shows a total displacement rate is between 60 to 130 mm per year, traveling downslope toward the river at the angle of 10 degrees with respect to horizon. The next slide is Red Hill. The results indicate that the toe of this slide is merely moving southward at the rate of 50 to 70 mm per year. This direction of movement for areas close to the river makes sense since we know that the outer curve of the river is being constantly eroded. Vectors obtained by SAR analysis also show that other parts of the slide are moving toward the river as we expected with rates of 10 to 20 mm per year. On the right you can see the vertical displacement rate, which shows that most of points are showing 0 to maximum 10 mm per year except for those near to the river. Unfortunately, not so many in situ studies have been carried out on this slide, so an extensive knowledge has not been accumulated for this case to compare our results with. But the studies in literature were found that looked at this site by employing single geometry in SAR. And our line-of-sight results were found to be a match with what they reported. Another study area that I worked on was the Oldman River Dam. It is in the south of Alberta, 80 km east of Lethbridge. The dam construction was completed in 1992, but the ongoing displacements of the spillway and its adjacent areas were identified from the very beginning of construction in 1986. Previous studies have reported several weak clay seams at different elevations with residual friction angle of 11 to 15 degrees. Alberta Ministry of Environment and Parks, along with other consultants, have installed sloping clinometers and extensometers to monitor the spillway displacement. In a comprehensive report prepared by the University of Alberta, long-term trends of displacement rates were established, reporting a decelerating trend toward a rate of 1 mm per year. For this case, only two geometries could be accessed, descending and ascending modes of Sentinel-1. As a result, we were only capable of obtaining two components of movement vectors, vertical and east-west. This was not an issue since, according to previous reports, the spillway movements have a very strong west-east direction. Figure 15a presents the horizontal displacement rates. It is noted that the positive sign indicates an eastward movement and the opposite is true for values with negative sign. As seen here, analyzing SAR images confirmed that the spillway and its adjacent areas are moving at rates less than 1 mm per year toward east. Most of embankment is also moving westward at the rate of almost 0.5 mm per year, but you can spot a confined area in mid-height of embankment with high rates, going up to 3 mm per year. Figure 15b also shows the vertical component, and it indicates that almost the entire area is moving downward at a very negligible rate, but it shows embankment is subsiding at rate of 3 to 4 mm per year, almost at the same hotspot location of horizontal movements. Alright, I believe that would conclude my presentation here, and these are the references I used for today's talk. Thank you very much for your attention. I'd like to especially thank David and Drew from Geological Survey of Canada, who worked very hard to provide us access to radar-sat images despite all the technical issues. Now I'd be more than happy to answer any questions you might have. Thank you very much.